there is a rule that governs everything in the universe. Not a suggestion, not a theory we haven't tested yet. A foundational assumption so deeply baked into our best models of the cosmos that if it were wrong, everything we think we know about the universe collapses with it. The rule is simple. At large enough scales, the universe looks the same in every direction. Matter spreads out evenly. No region is special. No structure is too dominant. The universe, at its core, is smooth. We call it the cosmological principle, and for decades it held. Then we found something, a structure so incomprehensibly vast that our models say it cannot exist. Not that it's unlikely, not that it's surprising, that it is mathematically, physically, fundamentally impossible under the rules we built our understanding of the universe on. It is 10 billion light-years across, and it is very, very real. To understand why this object breaks everything, you first need to understand the rule it breaks. The cosmological principle was not invented arbitrarily. It emerged from observation, from mathematics, and from one of the deepest assumptions human beings have ever made about our place in the cosmos. That we are not special. That Earth is not at the center of anything. That the Milky Way is not uniquely positioned. That wherever you stand in the universe, the view, at the largest scales, looks roughly the same. This idea has a name in physics: isotropy. The universe looks the same in all directions. Pair that with homogeneity. The universe has the same density and structure everywhere. And you have the cosmological principle, the two pillars that hold up almost every major model of the universe we have built in the last 100 years. The Big Bang model rests on it. The standard model of cosmology rests on it. Our calculations about dark matter, dark energy, the expansion of the universe, all of it assumes the cosmological principle is true. And for a long time, the evidence supported it. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, light that has been traveling for 13.8 billion years, it is almost perfectly uniform. Tiny fluctuations exist, but they are tiny. The universe at its earliest moment was smooth. As it evolved, matter clumped. Gravity pulled hydrogen into stars, stars into galaxies, galaxies into clusters, clusters into superclusters, superclusters into vast filaments of cosmic web. Structure formed. But the models predicted a ceiling. A maximum size beyond which structures could not grow, because the universe simply has not existed long enough for gravity to pull matter together across distances greater than a certain threshold. That threshold is roughly 1.2 billion light-years. That is the scale at which the universe should smooth out. Beyond that size, no structure should dominate. The rule says so. The object we found is 10 billion light-years across. It was not found the way most astronomical discoveries are made. There was no single telescope that pointed at it, no single image that captured it. You cannot photograph the Hercules Corona Borealis Great Wall. It is too large to see. It is too large for a single observation to even register it as one thing. It was found in data, specifically in gamma-ray bursts. Gamma-ray bursts are the most violent events in the observable universe. When a massive star collapses into a neutron star or a black hole, or when two neutron stars collide, the explosion releases more energy in a few seconds than our sun will produce across its entire 10 billion year lifetime. They are visible across the universe. We can detect them from billions of light-years away, which makes them extraordinarily useful as cosmic markers. Where gamma-ray bursts cluster, matter clusters. Where matter clusters, structure exists. In 2013, astronomers Istvan Horvath, Jan Hakila, and Zsolt Bagoli were analyzing a dataset of gamma-ray bursts when they noticed something wrong. A region of the sky in the direction of the constellations Hercules and Corona Borealis was producing far more gamma-ray bursts than it should. The clustering was not random. It was not noise. It was statistically significant in a way that demanded explanation. They mapped the distribution. What emerged was a structure roughly 2 to 3 billion light-years in diameter at first measurement, already uncomfortably large. But as they refined the data, as more gamma-ray bursts were cataloged, the structure kept growing. By later analyses, it had expanded to approximately 10 billion light-years across. To put that in context, the observable universe is 93 billion light-years in diameter. This single structure spans more than a tenth of everything we can see. It is the largest known structure in the observable universe, and it should not exist. This is where the physics becomes genuinely uncomfortable. Our models of cosmic structure formation are not vague. They are precise. We understand, with considerable confidence, how gravity works over cosmic timescales. We understand how matter behaved in the early universe. We can run simulations, enormously complex computer models of how the universe evolved from the smooth plasma of the Big Bang to the tangled cosmic web we observe today. Those simulations are good. They match observations across an enormous range of scales, and they produce a hard limit. The largest structures they generate are on the order of 1 billion light-years. Beyond that, the universe has not had enough time. Gravity is powerful, but it is not infinitely fast. To pull matter together across 10 billion light-years of space would require more time than the universe has existed. The universe is 13.8 billion years old. The structure we found spans 10 billion light-years. The numbers do not work. There are only a few possible explanations, and none of them are comfortable. The first is that we are wrong about the data. That the gamma-ray burst clustering is a statistical artifact, a coincidence, a flaw in the sample, a bias in how we detect these events. This is the skeptic's position, and it is a reasonable one. Science demands skepticism. The dataset used in the original 2013 paper contained around 300 gamma-ray bursts. That is not a small sample, but it is not enormous either. Except that in 2025, a new analysis was published. The dataset had grown to 542 gamma-ray bursts. The clustering did not go away. It strengthened. The statistical significance held. The structure remained. The second explanation is that it is not truly a single structure. That what we are seeing is a projection effect. Multiple unrelated concentrations of matter that happen to align along our line of sight and appear connected when they are not. This is also possible. It is also very difficult to rule out completely without a different observational approach. The third explanation is the one that keeps cosmologists up at night. The cosmological principle is wrong. If the cosmological principle is wrong, if the universe is not homogeneous and isotropic at large scales, then the foundations of modern cosmology need to be rebuilt. This is not an exaggeration made for dramatic effect. It is the literal consequence. Every major calculation we have made about the universe assumes homogeneity. The rate of expansion of the universe, calculated using the Hubble constant, assumes the cosmological principle. The age of the universe, 13.8 billion years, is derived from models that assume it. The proportion of dark matter to dark energy to ordinary matter that we believe fills the cosmos. Those numbers come from models built on this assumption. If the universe is not smooth at large scales, if there are genuine megastructures that our models cannot produce, then our models are wrong. And if our models are wrong, every number we have derived from them is potentially wrong too. This is why the Hercules Corona Borealis Great Wall is not just an interesting anomaly. It is a potential signal that something fundamental is missing from our understanding of the universe. There is precedent for this kind of revolution. In 1929, Edwin Hubble's observations of galactic redshifts showed the universe was expanding, a result that overturned the prevailing assumption of a static cosmos and forced physicists to rebuild their models from the ground up. In 1998, observations of distant supernovae showed the expansion was accelerating, something no existing model predicted. And the result was the introduction of dark energy, a placeholder for something we still do not understand, now representing 68% of the total energy content of the universe. Both of those discoveries came from data that contradicted the prevailing model. Both forced revisions that changed everything. The Hercules Corona Borealis Great Wall is that kind of data point. We do not yet know if it will force the same kind of revision, but we cannot rule it out. What makes this story particularly urgent right now is the 2025 dataset. For years after the initial 2013 discovery, the Hercules Corona Borealis Great Wall existed in a state of scientific limbo. It was real enough to publish, anomalous enough to generate debate, but not confirmed enough to force a consensus. The community was cautious, which is appropriate. Extraordinary claims require extraordinary evidence. The 2025 analysis changed the conversation. With 542 gamma-ray bursts mapped, nearly double the original sample, the clustering signal persisted. The statistical methods were updated. The potential biases were examined more carefully, and the structure survived the scrutiny. It did not shrink. It did not resolve into random noise. It remained stubbornly, inexplicably large. This does not mean the debate is over. Science does not work that way, but it means the anomaly can no longer be dismissed as a small sample artifact. The community now has to engage with it seriously. The question is no longer whether the data shows something unusual. The question is what that something is, and we do not have a good answer yet. To fully appreciate what we are dealing with, it helps to step back and look at the universe as a whole. The cosmos is not a random scattering of galaxies. It has architecture. Zoom out far enough and you see it. A vast three-dimensional web of filaments and voids. Galaxies cluster into groups. Groups cluster into clusters. Clusters link into superclusters. Superclusters stretch into filaments hundreds of millions of light-years long, wrapped around enormous empty voids where almost nothing exists. This is the cosmic web. It is the largest scale structure we can see, and it is beautiful in the way that something incomprehensibly large can be beautiful. A scaffolding that spans the entire observable universe, built by gravity over 13.8 billion years from the quantum fluctuations of the very early cosmos. Within this web, we have found remarkable things. The Sloan Great Wall, discovered in 2003, stretches approximately 1.37 billion light-years, close to the theoretical maximum our models allow. The huge large quasar group, found in 2013, spans roughly 4 billion light-years and itself presented a challenge to the cosmological principle. The Boötes void, not a structure but an absence, is a region roughly 330 million light-years across where almost no galaxies exist at all. An emptiness so profound it challenges our models of how voids form. Each of these pushed the boundaries. Each of them generated debate. The Hercules Corona Borealis Great Wall dwarfs all of them. It is not at the edge of what our models allow. It is not a modest challenge. It is an order of magnitude beyond anything our simulations produce, sitting in the data, demanding an explanation we do not yet have. The honest answer is that we are waiting. The Hercules Corona Borealis Great Wall cannot be confirmed or refuted with the tools we currently have deployed at full capacity. Gamma-ray burst mapping is powerful but indirect. What we need are more bursts, better localization, and ideally a complementary method of tracing large-scale structure in that region of the sky. Future surveys may provide that. The Vera C. Rubin Observatory in Chile, now operational, will conduct the largest astronomical survey in history, mapping billions of galaxies with unprecedented depth and coverage. The data it produces over the coming decade will either confirm or challenge what we think we see in the gamma-ray burst distribution. The Nancy Grace Roman Space Telescope, scheduled for launch, will add further depth to our map of the cosmos. We are also improving our gamma-ray burst datasets continuously. Every detected burst adds a data point. Every data point either strengthens or weakens the clustering signal. The 2025 analysis showed the signal strengthening. If that trend continues, if future datasets with 800, 1000, 1500 bursts maintain the clustering, the pressure on the cosmological principle will become very difficult to ignore. There is also a more radical possibility that some physicists are beginning to take seriously. Perhaps the cosmological principle is not wrong, but incomplete. Perhaps it holds across most of the universe, but breaks down in specific regions. That the universe is smooth on average, but harbors genuine large-scale anomalies that our current models do not account for. This would require new physics, new terms in our equations, new assumptions about how structure forms and grows. That is not a comfortable place for a scientific field to find itself, but it may be where the evidence is pointing. The universe has spent 13.8 billion years building itself according to rules we thought we understood. Smooth at the largest scales, homogeneous, isotropic, no single structure too dominant, no region too special. The cosmological principle, the assumption that has underpinned a century of modern astronomy. And then, in the data from the most violent explosions in the universe, in the distribution of gamma-ray bursts scattered across the sky, we found something that the rule says cannot exist. 10 billion light-years across. Larger than anything our simulations produce. Larger than anything our models allow. Still sitting there in the 2025 dataset, unresolved, unexplained, and stubbornly real. We do not know yet what it means. We do not know if the cosmological principle needs to be revised, rebuilt, or replaced entirely. We do not know what new physics might be required to explain a structure this large. What we do know is this: the universe has a rule. This object breaks it, and the universe does not care whether our models are ready for that.